Welcome to episode 4. We are going to attempt to finish chapter 1 as we press on in our epic journey through physics 1. And we're going to pick up right where we left off in the last video. So let's go right to our PowerPoint. Okay. The purpose of this video is to augment the class notes. Basically, you have all of the lecture notes. Let's talk about these two runners here. Okay, so two runners jog along a track. The time at each position are shown. Which runner's moving faster? Okay, so we have here 0, 1, 1, 2, 3, and 4. Okay, so it looks like this is their distance. So we need to look at the dots and we need to say, well, what is their position with time? Okay, the time in each position is shown. So we're missing a few dots here, but the position for both of these looks like it's about the same. So after 6 seconds here, they're both at 30 meters. So it looks like they are at the same. So yes, both runners are moving at the same speed, even though we only have half the number of dots. Okay, so watch in the book the video Putting Numbers on Lecture. They give a really good demonstration because everything in this class we're going to do is going to require units. We can't do a calculation unless we have units. We need to have a coordinate system to figure out our position. So we start here with an origin here in the middle, and that is our origin is going to be at position 0. Okay, so right here, that is the origin of our coordinate system, and we have negative numbers and positive numbers, and we also know that this is in the units of miles. Okay, in the United States, we always use miles, but these are not SI units. So this gives us a position, and so we can tell which way we are moving. And this is our coordinate system. So usually if we have a coordinate system, there's a symbol over here on right there that tells us what the coordinate is. We also have units here, so this tells us that it's in meter and in meters, and we usually have tick marks like this. So it could be 0, 10, 20. It could be different depending on the scale that we want to use. Then over here, the 0 is the start of our race, and then the final coordinate 50 here, this is the end of our coordinate system. So usually this is these are drawn to display a convenient idea. So you want to make sure that the scale of your coordinate system that you show matches what's happening. This image that you see in the background is actually the part of the Cone Nebula. It's NGC 2264, and it is a giant star-forming pillar. It's made out of gas and dust, and it lies about 2,500 light years from Earth. And this region here is an expanse that's 2.5 light years of in the picture. So it's only a piece of the nebula. The entire nebula is actually 7 light years long. 7 light years long. So what does a light year mean? Well, 1 light year is the distance that it would take light to travel in 1 year. So if light travels at 3 times 10 to the 8 meters per second, you can tell that that's actually quite a long distance. In other words, 1 light year is 5.9 trillion miles. That's quite a long ways, or 6 trillion miles. In physics, units are important, especially when we're dealing with objects that are really big, distances that are huge, like a light year, or things that are also really small. Units matter a lot. And most of the problems that we do, units are going to be very important. Besides units, we also need to talk about something very important called displacement. So displacement is a vector, and there's a big difference between displacement and distance. So if we were thinking about distance, then if we considered this picture here, let's say the person started out right here. They could travel down this way some distance and then over here. That would be the total distance that I traveled. But displacement is a vector, and so your displacement would always be a vector pointing to wherever you were at. And that vector would change depending on how far you were from where you started. So displacement is a vector, and it always has a direction. So there's always an angle here. So we could consider the angle here, or we could consider the angle the other way. So if we went the other way, so we would go around this way, okay? So we have one angle going that way, and we have another angle going down like this, okay? It's the same thing, but it depends on which way you draw the angle. So for example, if this angle right here were 30 degrees, then that would be going in the clockwise direction. If, on the other hand, we wanted to go in the counterclockwise direction, we'd say, okay, there are 360 degrees in a circle. So if I went all the way around the circle once, that would be 360 degrees. But here, I want to find my angle going counterclockwise. And so I would subtract it from the angle going clockwise. So it would be 360 degrees minus 30 degrees. That would give me a total of 330 degrees going counterclockwise. In the slide here, we're only going to look at a problem that's along the x-axis right here. So we start right here, and we've chosen our axis to have a convenience scale because the total trip is going to be 150 feet. So that's the end of our axis. Our origin would be right here at 0 feet. And so we start at 50 feet and we move to 150 feet. So this is XF over here and X initial. So to find delta X, that's the difference between, that's our displacement, and it's the difference between our final position and our initial position. So that's really important. So we take our final position and subtract it from our initial position. And that would give us a total displacement of 100 feet. In order to quantify the motion and to get to something that we'll call velocity, we need to consider changes in time and position. So if we look on the figure here, if this is our, so if our position is at, say, 0 right there, then we move over here to 20, move over here to 20, then to 40, and to 60. And we see here that between each of these dots for our motion plot, there's an equal distance in time. So 1 second elapses between each of these, and also the distance is the same. So we could say that this is an example of constant motion. Let's look at an example. So Emily's riding her bike in the country. and she is on a road that goes from east to west past a water tower. And the water tower is going to be the origin of our problem. So we need to define our coordinate system so that increasing x means moving east. So at noon, Emily is 3 miles east of the tower, and a half hour later, she is 2 miles west of the tower. Okay, so always draw a picture. There's our water tower, and I can draw my own coordinate system. So this will be 0, 1, 2, 3, 4. Oh, but I made it too big. I don't need, she's only moving 3 miles and 2 miles. So I can actually erase those. I don't need so many tick marks there. That's important because you want to draw your coordinate system to the scale of your problem. So instead of making those little ones, I'm just going to go 1, 2, 3, because she starts 3 miles east of the water tower. We're going to say this way is east over here, and she's going to end up 2 miles west of the water tower. West is this way, okay? So I'm going to draw 1, 2, 3 over this way. I can label these, of course, so I'll have 0, 1, 2, 3, and this will be -1, -2, and -3. So I'm going to put a symbol over here to represent that this is the x-axis, and we only need one coordinate for this problem. It's a one-dimensional problem. She goes from east to west, and our units are going to be in miles. Okay, so strategize. We'll use a particle model to represent Emily. She's riding along east to west roads. We'll make use of a one-dimensional coordinate system. Yes, instead of drawing a picture of Emily on a bike, we will draw Emily as a dot. There. Hi, Emily. How's it going? Okay, so Emily starts out over here. She's a dot, and she moves from 3 over here all the way to -2. Okay, so this is going to be her initial position, and then over here is going to be her final position. Okay, so then we can say delta x, there's delta x equals x final minus x initial. There's initial. Okay, so she started at x, or x final is -2. So we will have down here, delta x is going to equal her final position -2 miles minus, right, her initial position, which is 3 miles. Okay, so that means we've got our displacement is going to be delta x will equal -2, -2 minus 3 is going to give us a -5 miles. So does this point in a direction? The answer is yes, it has a negative sign. So that tells us that she is moving in the negative direction. So we will draw Emily at her vector here as green. Okay, so her vector is going to be green, and she is moving in the negative x direction, and the magnitude is 5 miles, and the direction is negative. So looking how they do it in the problem, the next step is prepare. That's what I did. I drew a picture, I drew my axis, and I have the whole thing set up. So the water tower is at position 0. That is our origin, and we choose our coordinate system with x increasing to the east. And that is usually the convention that you would use. So positive is always going to the right. Then we solved our problem, and we found that the displacement is -5 miles. Okay, Then the last part, we need to assess. So Carol is moving to the west. So we expect her displacement to be negative. Yes, it was definitely negative. So she started east, moved west, and we got it negative. So that makes sense. Okay, so let's look at the notes. They have a 4-step process in this book, which they really want to emphasize. So strategize. Think about, how am I going to solve this problem? What can I do? Then prepare. Always draw a picture. It doesn't matter if you're a good artist or not. Draw a picture. Use action figures or something. But that helps you to visualize the problem. Once you have prepared, you've drawn your coordinate system, you've set up your equation, then you can solve it. Then when you're done, assess it. Does this make sense? Am I getting something that sounds reasonable? If I ended up with something that's totally crazy, then you'll know that you did something wrong. And part of the assessing comes with experience. The more problems you do, the better you'll get, the more you'll know if this is something that makes sense or not. So let's practice what we've learned and do a quick problem. Maria is at position x equals 23. She then undergoes a displacement, delta x, which is minus 50 meters. What is her final position? Okay, so I'm going to draw a coordinate system that makes sense for this problem. So I will put this here, and I'll put my origin here. This will be 0, and I'll say that this is 25, and over here is 50. Then my coordinate system over here, this will be minus 25, and this will be minus 50. Okay, that's just what I picked. So Maria's going to be about here. All right, so she undergoes a displacement of negative 50. So that means she's going to go this way about, yay, this is my displacement, delta x equals minus 50 meters. Okay, so what this means is I need to take her initial position and subtract 50. So I have, let's write delta x here equals x of f minus x initial. Okay, so we can just flip this around. We can say x of f, it's still positive, no sign change, and delta x goes over here. I'm going to take my xi and move it to the other side. So this will be plus xi. Now we can put our numbers in there, and let's see if we get it right this time. Okay, so delta x is minus 50. It's math. It should make sense. Plus 27. No, that's the answer. My initial position is 23. So minus 50 plus 23 is going to give me minus 27. And this is in meters, minus 27 meters. So I will have, oh man, let's see, I'm doing it again. I'm talking. And sometimes when I talk, my hand writes something else, but that's okay. So that is going to be x final is going to equal minus 27 meters. And sure enough, the answer is, in fact, minus 27. Let's look at another example. An ant zigzags back and forth on a picnic table is shown. So he starts out at what looks like 40. He goes over to 15, back to 30, and then back over there to 10. All right, so the first part of his journey, it looks like he ends right about there. That is going to be what looks like 15. The second part of his journey, he goes from 15 back over to 30. So that's another 15. So altogether, we've got 15 plus 15. Then he heads from 30 all the way over to 20. So the final part of his journey is 20. So that means the total distance that he traveled is going to be 50, but his final displacement is going to have a different value. So initially, he starts out at 40, then he moves in the negative x direction to 10. So that's a total displacement of, it looks like, minus 30. So let's look at our choices. We know that his distance was 50 and he had a negative displacement of minus 30. So it looks like the correct answer is going to be E.
Thank you. Like and subscribe down below.